Of course, Professor Chung Kao is a familiar face here since he has visited frequently. I know Chung. When did we know each other? About the time you graduated?
Probably 1991.
91.
Or 92.
There was a snowman or something?
I don't remember exactly.
Okay.
I think for sure we met in Academia Sinica.
No.
Before that?
91 I was abroad.
Okay.
Okay, anyway, Professor Chung Kao received his degree from University of Texas at Austin in 1990. And since he's a frequent visitor, most people are familiar with him. So I think since we lost time, I'll just leave the floor to you, Chung.
Thank you. I want to thank George again for inviting me to visit NTU and also for making arrangements for this seminar. Today, I was thinking about having students in the audience, so I have about a third of my talk talking about tools and skills you may need to do research. But if we have mostly experts, I will speed up and talk about tools less. So today, I want to talk about Higgs pair production from gluon fusion and also Higgs pair production from bottom quark fusion. Those are different processes for different models. For the standard model, gluon fusion is the dominant process. For type 2 Higgs doublet models, bottom quark fusion will become important if we have a large tangent beta. After that, I will share some statements from Howard Georgi and Peter Lapage. And this is for the amusement for theorists, especially for George and Xiaogang, and also for postdocs and students. You may find their statements fascinating. Okay. And then I will discuss the trilinear Higgs coupling or couplings, depends on what model you are dealing with, and the effect of this possible coupling in Higgs pair production. Finally, I will talk about discovery potential of Higgs pairs at the LHC. I was hoping Mimura could be here because George told me that Mimura also did some studies on the Higgs pair production and Higgs self-couplings. But that's okay. You can pass on the message and tell him that I cited his research. Okay. What we have learned from ATLAS and CMS is we have discovered a spin zero particle. This particle behaves very similar to this Higgs boson that Weinberg described in his paper. And we have measured almost everything except, let's say, Higgs to light quarks and Higgs to TT bar. Maybe we can say Higgs to TT bar is well understood from glue to Higgs. However, there is one more thing we have to check. For Higgs to light quarks, there is no way we can check. But there is one more thing we can check and we need to, and that is how Higgs boson interact with itself. And that is the Higgs coupling. We call the trilinear coupling, and maybe many theorists are working on this topic, trying to make suggestions to our skillful experimentalists how to verify or test this coupling and tell us if all we have is the standard model or we can have some clues of something beyond the standard model. And I will tell you that there are big uncertainties when we try to understand this coupling. And this uncertainty can be as large as probably 40 to 50%. For next to leading order calculations, people claim the uncertainty is probably 20% within 1 sigma range. And I will tell you something published by the Wisconsin group, what they have found. So this is what I learned from the CMS webpage. That is, Higgs to BB bar agrees very well with the standard model expectations, and so is tau tau. Higgs to gamma gamma used to be right here. Now it moved to the other side. And I would like Kaifeng to tell us what was the change from one side, almost 50%, to the other side, and so close to 1.
Well, I think data was double, more than double data added. And well, surely the technique also changed. But it's hard to say. But in any case, Atlas is still keep at the other side, seems to go to the negative side. So how can I do?
Okay.
Atlas has a seesaw compared to this graph.
Okay.
I noticed you mentioned Wisconsin group, not an NTU group, or CMS. This was someone. This is not a CM completely without.
If you go to CMS website, you will see this.
Yeah, but why do you say Wisconsin group?
Oh, in the conclusion part, I will use some results from the Wisconsin group.
Theory or?
Theory.
Yeah.
Yes.
That's
Not experimental. Okay. So these two are the major discovery channels. We know now they agree with the standard model pretty well. And I like this figure very much. That is, it's probably fair to say we don't have to worry about fermions that don't like the Higgs boson, because all fitting within 95% confidence level seems to suggest all fermions love a scalar particle called Higgs boson. And of course, you can say this kappa T has asymmetry because it doesn't matter it's positive or negative. When you square, you get the same answer. And for this kappa V with this asymmetric shape, because it's 0.5 or 1.5, it's not the same thing as plus minus sign. It's more subtle, depends on statistical fluctuations and also systematic errors. But however, I find this CMS figure very, very impressive. We have learned a lot from experimental data.
But again, the statement is not the same from Atlas, right?
Right.
The Tata and BB are not supporting this.
That's true.
Yeah.
That's true.
So you cannot just select one experiment.
But so far, CMS data seems to be encouraging.
Okay, you're
In some
coming from an
sense.
Atlas Institute, so I appreciate that.
Okay, now let's take a look at this. And Kaifeng helped me to solve a problem that I faced with my postdoc when we were studying Higgs to BB bar. And I assume this mass shift is from the same reason. When a tau decays, when it was identified and reconstructed, it actually has lost a lot of energy. Therefore, the reconstruction with 2 neutrinos missing or 1 neutrino missing is non-trivial. Therefore, we do not expect Higgs 2 tau tau will give us m tau tau to be close to 126. This is where we should have, and this is whatever is observed. But 6 GeV is not too bad. Thinking about missing energies in the final state. In the simulations I did with my postdoc for Higgs to BB bar, we saw a 15 GeV deviation. From 126, we saw 126 minus 15. So it was about 111. But the day before yesterday, Kaifeng was able to reconstruct the Higgs mass and show us the correct peak again. So this is something, if you are a theorist, do not trust any theoretical tool without independent check. Don't say, it's simple, I put in my model, I worked for 3 months, I have a paper. It could be a blessing to you if it is correct, but it could also be a curse if you trust the tool too much without checking. It could give you wrong answers.
But that was BB bar.
Yes, but Tata, I expect something similar.
Probably which
Well,
one?
this is wrong is because the package has a problem, or the guy actually using the package don't know what to do.
I guess the guy using the package doesn't know what to do.
That's different.
Okay, so we know how to calculate Higgs pair production. From gluon fusion, if MH is less than 500 GeV, then gluon fusion is most important. It will go through triangle and box diagrams. And the triangle diagram will have Higgs self-coupling, however the box diagrams do not. If we have heavy Higgs, now we don't expect a heavy Higgs similar to our standard model Higgs. However, there might still be a heavy scalar if we have a decoupling limit such that one light state will behave like the standard model Higgs, but another state will be heavier. In that case, vector boson will not work, because this statement is true only for the standard model. If you have a two Higgs doublet model, in the decoupling limit, one Higgs boson behaves like the standard model, the other will decouple from gauge bosons. Therefore, vector boson fusion will not work, because if we parameterize the coupling in terms of sine and cosine, the light Higgs will behave like sine beta minus alpha approaching 1, and the heavy guy will approach like cosine beta minus alpha that goes to 0. Therefore, this is correct only for the standard model, not for a two Higgs doublet model in the decoupling limit. So let me show you fundamental diagrams. This is the box diagram without trilinear coupling, and this is the triangle diagram with a Higgs, trilinear Higgs coupling. And for completeness, this is another well-studied channel to look for trilinear coupling.
So these two classes of diagrams, which one?
This
A
one.
and B. A.
Yes.
In LHC, right? I mean,
Correct. So these are more important. Of course, I should say, actually, this is the dominant process. So let's see. So we have a box. I should not say we have a box. We have a set of box diagrams that contribute to this dashed line in green. Then we have a triangle diagram with Higgs coupling, a trilinear Higgs coupling that is represented by the dashed line. Then we have the total. You can see the destructive interference. And this is scale dependent. Therefore, if we choose MH, this is the expectation. If we choose half of the MH as suggested by BB bar studies, then this is what we expect for gluon fusion to generate two Higgs. Now, this is back to Xiaogang's question. This is glue. This is vector boson fusion in this, let me see, in this funny purplish line. Okay. And so this is QQ bar to HH with WW. And this is QQ bar to HW with a pair of H. So you can say these are negligible. And this is important. TT bar is important until energy is raised. Then WW fusion becomes important. So it's safe to say at 8 TeV up to 14 TeV, we can just calculate gluon fusion, and we have the dominant piece of contribution. And a group of courageous people, this fellow, if he is the fellow that I know, Daniel, I was on sabbatical in Slack, and he was the afternoon coffee break cop or police.
Oh.
Every day he knocked on every door, including Bill Ken. If he shows up, he will say, "It's coffee time, come and let's have coffee and chat." So this Daniel is very tall, almost as tall as 2 meters, I think. Okay, and I have not met this guy. They did next to leading order calculations for a 126 GeV Higgs. They found the cross section is 9.8 or 40 for 14 TeV, 243 for 33 TeV, and for this very high energy collider, it's more than 1600 femtobar. And they also listed the uncertainties. And during this trip, I asked Kaifeng a very interesting question, because I used to think most experimentalists will say, if we have uncertainties, let's add them up in quadrature. Until the Higgs group at CERN said, if they are correlated, don't do the quadrature addition. That's silly. That's not correct. If they are corrected, if they are correlated, you should add them up. So a correct practice should be, let's add the scale dependence and the PDF plus alpha S dependence together to get the uncertainty. Do not add them like quadrature. So at 8 TeV it's 18%, at 14 TeV it's 15%, at 100 TeV it's about 12%. So the uncertainty, if they are correlated, we should add them together.
It should depend on the correlation.
We know that PDF depends on scale, alpha S depends on scale. So if each has some uncertainty, and alpha S probably is correlated with PDF because each PDF set will choose a set of parameters for you to calculate alpha S. So that in some sense they depend on each other.
Right, but how can you add them linearly therefore?
Yeah, that's.
Oh, okay. So what's your suggestion?
You have to study the correlation.
Okay.
It's a correlation matrix,
Okay.
right?
So you brought up the question.
Okay, okay. The Higgs.
Adding linearly is, what is it? It's
100%. 100% positively correlated. You add linearly, but it can be not 100%. So in this case, it's hard to say.
So maybe it's very.
Or you can negatively correlate.
Yeah, then it might be destructive too.
Yeah, you have to subtract. So it's hard to say.
Yeah, right. So it depends on the correlation.
Yeah.
So I guess this may be some interesting question for courageous young people to spend some time to
But
figure out.
finally, what does the,
I
since you
think
call the
experimental is better to do.
But these are theoretical uncertainties. There will be experimental uncertainties. And now let's take a look of leading order in dotted line or short dash, and next to leading order in longer dash, and then we have next to leading order in solid. So you can see the K factor actually is very impressive. Most people are using 1.8 or 1.9, but these two fellows, they found at 14 TeV, the K factor is about 2.3. And at 100 TeV, the K factor is about 1.7. So this K factor is a function of the machine energy. Okay, next topic is BB bar fusion. This is not important in the standard model, but it will be very important in two Higgs doublet models if it has type 2 Yukawa interactions. For tangent beta greater than 5, this will become the dominant contribution. So we have BB bar to 2 Higgs that has the trilinear coupling and these two without. So let me briefly go over this for the sake of postdocs, how we do QCD corrections. But I'm not saying all of us should do QCD corrections. Tini Wertmann will tell you, you need a physics reason before you do time-consuming calculations. Don't just say, oh, I have time, and this needs to be done, so let me do it. You must find a physics reason behind it before you spend a lot of time to do very messy calculations and with very little return. Okay? For this one, we were hoping to see if tangent beta is large. In type 2 Yukawa interactions, how can we determine BB bar to HH? And you can tell the NNLO has a K factor of about 1.5. And compared to glue, I must mention this is actually the physical process because we get all the B's from gluons. However, if we just do a simple leading order calculation of glue to BB bar HH, that's not correct because you do this only if you want to tag the B's in the final state. If you don't, if you tag one B, you should do B glue to BHH. If you don't tag any B, you should do BB to HH because the other two B's do not matter. So let's talk about alpha S corrections with real emission, alpha S corrections with virtual correction, and also here is the piece I mentioned. when you do glue to BB bar HH, there is something that can be large. MH over MB is not a small number. However, fortunately, we take the log, but compared to alpha S, this is a large number. Okay? And for glue to BB bar HH, then we have 1 over lambda squared. This becomes troublesome. So we should use running coupling. When we say constant, I think most of us know it's not a constant. It's a function of energy or a function of scale. And since we run alpha S, we also run masses. We have two types of masses, one called whole mass that Kai-Feng and collaborators tell us, or George, when he joins the meeting and asks people, tell me what is the physical mass. That's the whole mass you measure. But when you have calculations, usually we should use running mass. Means it's not a fixed number, it should be a function of scale, like what we do for alpha S. This room is becoming quite warm. Oh, I also teased that this room is as uncomfortable as the theory seminar room in CERN. So hopefully this room will generate great physicists, like what CERN has done. If you go to the CERN theory seminar room, maybe you have some measure of discomfortness compared to this room when you sit down and listen. Okay, so we use partial model to calculate, and it's an inverse process of factorization. Factorization is also called hadronization. That is, a quark will become a hadron, or a gluon will become a hadron. Partial distribution functions are fitted according to the inverse process. That is, how can we find a quark inside a proton? Now, the rule of thumb to remember is at high energy, x is the momentum fraction of p parton over p proton. So at high momentum fraction, we have a lot of up quarks and down quarks. At low x, we have a lot of gluons. That's why we like gluon fusion at high energies. The higher the energy, the better, because you have more gluons. You are going to generate a lot of things that you want from gluon fusion. So this is the gluon fusion, the gluon parton distribution functions. And right here we have what we call the C quarks that are SS bar and CC bar. Most people nowadays will tell you S and S bar may not be exactly the same, and C and C bar are probably the same. Okay. Now we have the tree level calculation, and then we have next leading order corrections. I would like to mention that there is something called infrared safety. Later, next page, I will tell you. That is, in doing all these, there are three singularities we have to deal with. The first one is most intuitive, is ultraviolet divergence at high energy. You need renormalization. Then, infrared divergence, you need to match the real gluon emission with virtual gluon contribution. And in dimensional regularization, one piece of 1 over epsilon will be positive, another piece will be negative. They just happen to be equal with opposite sign. They cancel each other to cancel infrared divergence. And collinear singularity is more subtle. We need to modify particle distribution functions to get rid of them. So this is the Lagrangian for QCD, and including what we need to produce a Higgs from BB bar fusion. And so now, as this real emission gluon becomes soft, becomes with an energy approaching zero, we call infrared divergence. But if this gluon has a momentum that is parallel to this quark or this quark, then if we treat mass as zero, we have collinear divergence. So let's go slowly. So now we have real emission that is proportional to alpha S. And since most parton distribution functions are valid only when partons are massless. So we take what most people practice with MB to be 0. And then we have the virtual correction because they don't show up in the final state. They are intermediate states, so they are virtual. When you take K to be infinity, this is ultraviolet singularity. We need to renormalize it. We need to renormalize this vertex, and later I'm going to tell you we also need to renormalize the Yukawa coupling. Okay, so next we deal with virtual corrections, and we find out the infrared divergence, and we use a nice tool we have learned in graduate school, that is dimensional regularization. We learned this from 't Hooft and Veltman. And usually if this is a class, I like to tell some stories. So someone told me that when 't Hooft went to graduate school in Netherlands, he went to this school with his uncle. His uncle was also a physicist at that time. So he went to his uncle and said, "Would you please take me as your student?" His uncle said, "No. For your sake, for your bright future, you should go and visit Professor Veltman. He is much better than I." So his uncle is wonderful. So he went to see Professor Veltman, and Veltman gave him this very hard problem. And for the first year, he thought it was not very rewarding. It's hard without going anywhere, so he was upset. However, he was very good in math, and he was very good in many things. So he was able to work out some satisfactory results, and in 1971, he and Veltman proved the renormalizability of the Weinberg model that even Weinberg himself gave up. So 't Hooft has a wonderful experience with Veltman, and of course later he moved on to many other branches of physics. But dimensional regularization and renormalization of the standard model was his first achievement. Okay, so now we have ultraviolet divergence and infrared divergence. And you may want to ask me, if I take a look at this formula, which one is ultraviolet, which one is infrared? Which one is ultraviolet? Can you tell? Actually, you don't have to say it. They don't have to be distinguishable. Since we are treating n equals to 4 minus 2 epsilon, this can come from loop integrations, this can come from phase space integrations. Therefore, this is the drawback of dimensional regularization. And later I will say more about this. But the lesson is, this KLN theorem, Xiaogang and George correct me, we know this as the KLN theorem, that is Kinoshita, Lee, and Nordenberg. They demonstrated if a fermion is massless, such as in QED, if you treat ME equal to 0, then the real photon or the real gluon will develop a infrared divergence, and the virtual gluon or virtual photon will do the same thing. Fortunately, the divergence will be cancelled when we add them together. So this is called the KLN theorem. Some people seem to suggest there was another group of people should deserve the credit. But so far, I think most people, when they teach perturbative QCD, they will mention this is KLN theorem. Do you agree? Here. So you can see, here is a negative 1 over epsilon, and but this is collinear singularity. We were supposed to have 2 more 1 over epsilons, one positive, one negative. One from space-space integration with a real gluon, and the other from the virtual. They cancel. So that gives us the infrared safety. But we still have this collinear divergence we need to deal with when we combine with parton distribution functions. So we modify parton distributions